rows, no belt, adult belt, children's car seat belt, and we had 2 columns, survivors and fatalities. We could create and calculate the probabilities for each cell based on the marginal frequencies. So the row and the column totals. And you have your joint probabilities if the 2 variables are independent. Okay. So as you see here, so you've got, this is assuming independence, what would you expect? And so let's see, we have for the joint, calculating the probability of A times the probability of B. For no belt and survivor, what you see is the 1638, which is the total number of non-belt, divided by the total number of children involved. That was the 3015. Probability of A, which would be the probability of no belt, times the probability of B, which is probability 2294, which is the number, the survivors, divided by the 3015. So that would probably be the probability of B, that they were a survivor. So probability that they were a no belt times the probability that they were a survivor. That turned out to be 0.413. And you could do this for each cell. Look again, so children's car seat belt and fatality. So this is a cross-check on that. So how do I get the probability of a children's car seat belt? That's 872 divided by 3015. How do I get the probability of fatality? That was 721 over 3015. Okay, so this is what I would expect based on, these are, you know, basically, this is, if they were independent, these would be the probabilities. Okay, if they met the probability A and B is equal to the product of those two numbers. So use the probabilities assuming independence and sample size to determine expected values for each cell in the contingency table. All right, so that would be the 0.413 times 3015, and you would have expected to see 1246. You would have, so in that first cell, no belt and survivors. But what we actually saw was 1129. You would have expected to see, if they were really independent, no belt and fatality. And again, these numbers, these probabilities are coming from the previous one, 0.413, no belt and survivors, no belt and fatalities, 0.13. And so we take that and we say, okay, if they truly are independent, then we would have expected to see in the no belt fatalities cell, we would have expected to see 392. What we actually saw was 509. So you go through and you're looking at that, and now you see expected versus observed. And here we go with the test statistic again. You compare the observed values from the expected values. Expected being computed based on were they independent or not. Expected being we assume independence, and let's go look at what our sample, what we actually came out with. And depending on your level of significance defined, you calculate what this value is across those. In this case, if we were looking at it, we would have 1, 2, 3, 4, 5, 6 observations for each of those cells, right? And we would add up those differences. And then identify whether that chi-square statistic value is greater than or within an acceptance region for the null hypothesis that they are indeed two independent. So here's learning checkpoint. Use the contingency table with the observed and expected frequencies to determine whether or not you would accept the hypothesis that the seatbelt status and the survivability in car accidents are independent. Use alpha equal or level of significance equal to 0.05, and note that there are number of rows, 3, minus 1, times number of columns, 2, minus 1, or 2 degrees of freedom for this chi-square test, or using that chi-square test statistic. Okay, So that is another sweeping brief look at something regarding testing for independence. Again, just kind of another form of hypothesis testing with a different focus to it. And in total, I wanted to go through and just kind of sweep through these different areas, different ways that hypothesis testing is useful and certainly used quite a bit in a lot of engineering by statisticians in engineering and business and large organizations in general to do their analyses. So this concludes this recording session. We'll see you at the next one.